This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, your professor for this class, and we're at Lecture 54. We're talking about lithography, and a second lecture on development where we discuss the concept of resist contrast. Photoresist contrast is a topic, a measure of the quality of resist and the process of development. That's been around for a long time. In fact, the contrast curve is sometimes referred to as an HD curve. Now, the first time I heard this term, I had no idea what it meant. People in our business like to use acronyms without explaining what they mean. Hopefully I don't do that too often in this class. But the first time I saw this at a conference, I thought, HD, what could that possibly mean? Oh, this is a plot of resist height versus exposure dose, HD. That must be what it means. No. Nothing to do with that. It's called the HD curve as a reference to the Herter-Driffield curve, because two scientists, Herter and Driffield, published a curve like this for the first time in 1890. It was a way of characterizing photographic negatives, and of course photography in those days was a relatively new technology. So the Herter-Driffield curve of those days plotted optical density versus dose on a log-log scale. Here we plot resist thickness remaining after development versus dose. And while we plot the dose on a log scale, unfortunately we chose to plot the relative resist thickness on a linear scale, although they made it a relative resist thickness, so close to a real HD curve. Nonetheless, this became a popular way of characterizing development and photoresist in general, especially in the early days of lithography. It's also called the characteristic curve. Some people call it the E0 curve. The experiment is quite simple. We take a large open frame area. We put a blank glass mask or fused silica glass mask in the stepper or scanner. We expose a large open area, then at a certain dose, and then we develop for the standard development process, the standard amount of time. And when we're done, we measure the thickness remaining in that open exposed area. We plot it on a relative scale, so the original thickness would be 1 on this scale, and we plot the exposure dose or exposure energy on a logarithmic scale. And then we look at the dose versus, thickness versus dose. And we get a highly nonlinear result, even on this exponential scale. At very small amounts of dose, we get very little change in the resist thickness. Then all of a sudden we hit a certain point where kind of a relatively threshold-like behavior, we begin to wash away the development, the resist, and we quickly move down to no resist remaining. This was thought to explain a lot of the nonlinearities, the behavior of the photoresist that we're trying to achieve. The intercept, the x-intercept of this curve, is called E0, or the dose to clear, or the clearing dose. This is an important parameter to know. It has something to do with the sensitivity of the photoresist. This is the smallest amount of energy you can give the photoresist and get it to wash away in the clear areas. It's not the dose to size, the dose that gives you a feature size that you are trying to achieve. That dose to size is always higher than E0, but it still tells you something about how sensitive your photoresist is. But the most important parameter we grab from the HD curve, or the characteristic curve, is the slope. Now the slope of this region is reasonably linear on this logarithmic scale, but technically we define the slope as we approach the intercept as minus gamma. Gamma is a letter in the Greek alphabet that we use to represent this slope. We call it the photoresist contrast. Gamma, in fact, is the letter that Herder and Driffield used in their original 1890 paper, and we continue to use in that tradition that same letter to represent the slope. Now the slope varies, as you can see, as a function of energy. It's not a constant slope, but there's a region here where it looks kind of straight, so we tend to try to fit it over some small region or technically as it goes to zero thickness. Now, of course, a logarithmic scale can be base 10 logarithms or base E logarithms, and that changes the value of gamma by a factor of 2.303. So we have to be careful about which scale we use and to explain to whoever we quote this value to which scale we use. Now, most people in industry talk about a base 10 value for the scale, partly because it's easy, but also partly because the value of gamma that we get is 2.3 times higher than if we used a natural log scale. I like the natural log scale. It is more useful to have a value of gamma based on a natural log scale, and that's the scale I will be using, despite the fact that my plots show a base 10. All of my calculations of gamma will employ a natural log scale. Well, the idea is very simple. Higher values of gamma are better photoresists. After all, the idea is that we want a region where all the resist remains and another region where all the resist washes away. And you would imagine that if I had a step function here, I would have a perfect developer. An infinite contrast corresponds to perfect dissolution discrimination between exposed and unexposed regions. Once I reach an exposure energy of E0, all the resist washes away. But below that energy, none of the resist washes away. That's the idea behind this slope. So gamma became associated with the idea of high contrast, or high quality. The idea of high contrast became associated with high quality in the photoresist. But then there was a problem. So I'll give you a little history lesson. In the late 70s, people began playing with track development, and in order to make track development work, one at a time wafer development, where we spray the developer on the wafer, we needed to add surfactants into the developer in order to get good wetting of the developer over the surface of the wafer. But of course, people worried about adding some kind of a extra chemical into the developer. It might affect the performance of the resist. So the first thing they did was they went out and measured the contrast of the photoresist. And they found something interesting. By adding surfactant to the developer to improve the wetting, they unwittingly improved the contrast of the photoresist. So developer A with no surfactant has a gamma of 1.2. Developer B with surfactant has a gamma of 2.4. Twice as high. What could be better? We solve the wetting problem and we improve the contrast. In fact, this inspired people to add more surfactant to the photoresist. The result was the contrast doubled again. In fact, the more surfactant you add, the more gamma improves until you get essentially a step function behavior. Well, that all sounds very good, except when they went and did real lithography, when they printed features, and they looked at their ability to control the feature size, and looked at the depth of focus, and things called exposure latitude, which is the how much the line width changes when you have a small error in exposure dose. They found that these higher gamma developers did not produce better lithographic results. And in fact, when they looked at resolution, maybe the most important aspect of gamma, higher gamma was supposed to enable higher resolution. When they looked at resolution, they found there was no improvement in resolution as gamma got bigger. This became very discouraging, and by the early 80s and in the mid-80s, people began to give up on the idea of contrast as a metric for photoresist quality. I'd like to explain the reason for this dilemma, the reason for this paradox, why we thought higher gamma would mean better lithography, but in fact higher gamma did not mean better lithography for the case of adding these surfactants into our developer. To do that, we have to delve a little bit more closely into what gamma is and what it means. And in fact, I'm going to define a new value of gamma. The real idea here, the real idea we're trying to get at, is to understand the nonlinearity of development rate versus dose. Now, we already saw in the last lecture that we want nonlinear development. And we looked at development rate versus inhibitor concentration and found that there was a parameter, the dissolution selectivity parameter N, which controlled that nonlinear behavior. But even without that model, without that idea, we can easily look at the impact of exposure dose on development rate. And in fact, this is very analogous with the original Herter-Driffield curve, which plotted log of optical density of a photographic negative versus log of exposure dose. But here, we are exposing with the purpose of changing the solubility of the photoresist. So the response that we're interested in understanding is how exposure dose affects development rate. This is a plot of development rate versus exposure dose. It is measured using something called a development rate monitor. This is a tool that can measure in real time the thickness of the photoresist as it is being developed. And because of that, we can extract from that thickness versus time curve development rate. And development rate can then, by varying the exposure dose, we can calculate the development rate or measure the development rate for different doses and plot them on this log-log curve. Then gamma, what I'll call the theoretical contrast, to differentiate from the conventional way of measuring the contrast we just mentioned, this theoretical contrast will be simply the slope of this curve. Now, the slope of this curve varies with exposure dose. So gamma is a function and not a specific value. But that's easy to deal with. The important point is we have now a definition of contrast that is dependent upon a fundamental response of the photoresist. How does the resist development rate respond to exposure dose? So the definition of theoretical contrast is d log r d log e, a slope on a log-log scale. Note that if I use natural logs or base 10 logs here, it doesn't matter because both of these, as long as these two scales are the same, any factor or multiplicative factor will cancel out. I'll use natural logs because it's more natural. So the theoretical contrast, d log r, d log e. It's a function of dose, so sometimes we quote the maximum value. But a better way to think of it is gamma theoretical is a dose-dependent function, and we would like to know what the whole function is. But even if we just quote the max value, that's better than what we've done in the past. My questions are, how does this definition of theoretical contrast relate to lithographic quality, and what is the relationship of theoretical contrast to measured contrast? The first question is quite important because without a good definition of what we are measuring, what we're extracting as a parameter, we can't relate it to lithographic quality. And without a direct relationship, we don't know that maximizing gamma is the same thing as maximizing lithographic quality. Let me give you an example. If we don't do a good job of defining our terms, we can come up with some ingenious but incorrect results. For example, what's the definition of your weight? Well, somebody who studied physics will understand that your weight is the force of gravity on your mass. But another way of defining weight not a very good way, but another way would be the number you get when you step on a scale. Now, for most of us, that's a perfectly valid definition. What other definition would we even need? The number I get when I step on a scale. It's my weight. But that's not the definition of weight. It's a measurement technique. And the reason it's important to differentiate between those two is that sometimes measurements fail. And if we don't keep track of when measurements fail, we won't know that it's a problem with the measurement versus a problem with the definition. So, weight, the number I get when I step on a scale. That's a valid definition under most circumstances, but what happens, for example, if I stick my scale in the back of a pickup truck, and then, just as I'm going over the top of a hill, I look down at the scale and measure my weight. What do I find? Oh my God, I just lost 20 pounds. I like that. I didn't even have to exercise. Did I lose 20 pounds when I went over that hill? No, of course not. I didn't lose any weight. I simply made an error in the measurement because the measurement failed, since it was now measuring both the force due to gravity on my mass and the centrifugal force of going over the hill in that pickup truck. The point is, if I defined my weight as the measurement I got when I stepped on the scale, then by definition I did lose 20 pounds when I went over that hill. This is like photoresist contrast. If we define contrast as the number we get from that measurement we made earlier, using the Herter-Drift field curve, the characteristic curve of the photoresist, I will get the wrong answer and I will never know why. But if we define contrast in this theoretical way, like this, and I figure out why it's related to what's important to us, lithographic quality, then I can figure out what went wrong with the previous measurement. And that's what we're about to do. So first of all, given the definition of photoresist contrast right here, a very simple manipulation. Multiply d log E onto this side, divide both sides by dx. What I find is something that looks like this. I'll try very briefly to explain the significance of this equation. D log R dx. This is a development rate gradient. What we want is a region of resist that has high development rate and a region of resist that has low development rate. And in between those two regions, I want a steep gradient between high and low development rates. This results in good lithography. So I want d log R dx to be high. So what is d log R dx? It's a function of two things. One, the theoretical contrast, multiplied by the second thing, d log I dx, where I is the intensity of light that I'm using to expose my photoresist. The intensity of light varies with position x because we're exposing with an image, an aerial image that propagates into the photoresist. D log I dx is the slope on a logarithmic scale of the aerial image intensity. And if I have a steep aerial image intensity, I get a steep development rate gradient. How steep? Well, whatever this gradient is, amplified by, multiplied by the theoretical contrast. This now tells me why high gamma is a good thing. If I have a large gradient of my image, I can get by with a low gamma and still get good results. But if I have a low gradient, in order to get a steep gradient in development rate, I need a high contrast in my photoresist. Here's an explanation of why large gamma is a good thing. This equation is called the lithographic imaging equation. It tells us both the impact of the image and the photoresist on the final result. It doesn't quite tell us everything, but it's a useful equation to understand. Now I have an explanation as to why high values of gamma theoretical result in good lithography. My next question is, how does this measure of contrast compare to the old measure of contrast, the conventional measurement? So let's go back to the conventional measurement. Remember, we had relative resist thickness versus exposure dose on a log scale. We had a curve that looked like this, and then we measured the slope as it reached the bottom. All right. So if I let tau be the relative resist thickness, then d tau d log e, I'll use a natural log scale here, at e equals E0, that is the dose to clear this point here. And then, tau is the resist thickness remaining, d is the original resist thickness, so d tau over d is the relative resist thickness, which is the thing I'm plotting, and boom, that's my slope. That's my slope, and this is the measured value of gamma. Actually, I think I have to throw in a minus sign. Since the slope is negative here, I throw in a minus sign right here because I want my gamma value to be positive just by convention. All right, that's the measured contrast. Well, can I compare the measured contrast to the theoretical contrast? We can. Let's start with the definition of development rate. Development rate is dz dt. If I'm doing a standard contrast curve measurement, I'm developing normally. That is open area exposure. The thickness of the resist just moves down as I develop. If z is the thickness of the resist, dz dt is the development rate. Then, if I move the dt over to this side of the equation, take the r, divide it onto the other side of the equation, integrate both sides, I get the integral of dt from 0 to the final development time, that's just development time, equals the integral from 0 to the depth down, z actually is the depth into the resist, not the thickness of the resist. I think I said it wrong originally. So integral from 0 to the depth down into the resist that I finish at the end of the development of dz over r. Okay, that is simply an equation that describes the development. Now let me take that equation and take the derivative of both sides with respect to log dose. I'm using log dose because we're going to use a log scale, and that just makes it more convenient. And if I take the derivative of both sides of this equation with respect to log dose, I find that I can relate the measured contrast to the theoretical contrast. And I do so with this equation. What does it say? The measured exposure dose equals the development rate at the bottom of the resist divided by the thickness of the resist. And I integrate from 0 to the full thickness of the resist, that is, integrate until I reach the bottom, of the theoretical contrast times dz over r. What has that taught us? Well, it's just an equation so far, but if we look at it, we can learn something about the relationship between these two parameters. Suppose I made the simplifying assumption that the development rate r did not vary with depth through the resist. That is, from the top of the resist to the bottom of the resist, development rate was completely constant. What would that mean? That means this r is a constant, and I pull it out of the equation. And in fact, r through the resist is the same as r at the bottom of the resist. And bottom is z equal d. These two things are the same number, and they cancel out. If r doesn't vary, then gamma doesn't vary. Gamma can come out of the equation. The integral from 0 to d of dz is simply d, and the d's cancel here and here. The result? Gamma measured equals gamma theoretical. In other words, my old way of measuring it, using the characteristic curve, relative thickness remaining versus log exposure dose, produces the same answer as my theoretical definition of contrast whenever the development rate does not vary from top to bottom of the resist. This is the key finding here. In other words, the assumption made in the conventional measurement technique is that development rate is not changing from the top to the bottom of the resist. It also means that anything that does change the development rate from the top to the bottom of the resist will cause an error in the measurement of the contrast. If what I really want to measure is the theoretical contrast, my measured contrast will only be the same as the theoretical contrast under these very strict conditions. Now let's look at some possibilities where the development rate does not vary, that actually does vary from top to bottom of the resist. Suppose I have absorption. What does absorption do? Absorption lowers the intensity of light from the top of the resist to the bottom. Lower intensity of light at the bottom means less chemical change, which means for a positive resist, lower development rates at the bottom. So R at the bottom will be smaller than R of Z everywhere else. This ratio of R bottom to R of Z will be a number less than 1. So gamma measured equals gamma theoretical times a number less than 1. In other words, my measurement technique will underestimate the value of gamma theoretical in the presence of absorption. Newsflash, all resists have absorption. Therefore, the measurement technique always gives the wrong answer. But it's even worse than that. The measurement technique can give the wrong answer in the presence of surface inhibition. This goes back to our discussion of the surfactant. One of the things surfactant does when I add it to developer is to inhibit the dissolution rate of a thin layer at the top of the resist. I get a layer at the top of the resist that just dissolves very, very slowly. And then once I break through that top layer, it develops normally. In other words, the development rate at the top of the resist is very, very small, sometimes orders of magnitude smaller than the development rate at the bottom of the resist. So, in the presence of surface inhibition, measured contrast equals theoretical contrast times a number bigger than 1. In fact, it can be much bigger than 1. If I add a lot of surfactant, I get a lot of surface inhibition. Development rate becomes very, very small at the top compared to the bottom. And gamma measured becomes large even if gamma theoretical does not change at all. And this is the problem that we had. Adding surfactant increases the surface inhibition phenomenon, lowers the development rate at the top of the resist, and causes the measured contrast to deviate markedly from the theoretical contrast. Well, this is not a good thing, and what we need to do is do a better job of measuring theoretical contrast using a development rate monitor to get at this number directly instead of the old measurement technique. All right, given that we've now resolved this paradox that deviled the industry for a number of years, let's move on to using our theoretical contrast. One of the ways we can use it is to calculate the theoretical contrast given a certain development model. Last time, we derived a development model. Here it is. This is the MAC model, kinetic model of development rate, where the development rate is a function of 4 parameters, Rmax, Rmin, N, and the threshold development or threshold inhibitor concentration, M threshold. Given some parameters, we can look at how, say, N affects gamma, the theoretical contrast. And what do we find? Well, here's the gamma versus dose, or gamma versus inhibitor concentration, little m, for n equal to 5. We find that we reach a peak value of the contrast at a certain level of exposure, certain level of inhibitor concentration, and that peak value is, it's about 4. So it's a little bit less than n equal to 5. If n equal to 10, the peak value is higher, but it's about 8, and it occurs at a higher exposure dose, that is a lower relative concentration m. And if n equals 20, I see that the peak value of gamma is about 16, still about 80% in this case of the value of n, the dissolution selectivity parameter. And the value occurs at a peak that is approaching M threshold. So you can see that as I go to higher values of N, the peak gets higher. The range of doses over which I get a high gamma gets smaller, and I begin to approach the theoretical, the threshold value of M as the place where this peak occurs. This says a couple of things. First, it says gamma is simply another measure of resist quality, and it's directly proportional to N. So higher values of N, the dissolution selectivity parameter, means the same thing as higher values of gamma. But that's not the only thing going on here. There's also a dose dependence, a dependence on the relative inhibitor concentration. And it says when I have a high value of N, I need to use higher exposure doses to get high values of gamma or contrast. So let's review what we've learned so far about photoresist contrast. First, theoretical contrast converts the image log slope, a measure of the quality of the aerial image that we're using to expose our resist, into a development rate log slope, which is a measure of how good our final developed photoresist pattern will look like. So higher values of contrast and higher quality aerial images produce higher development rate gradients. Measuring the contrast is very, very difficult if we want to use the conventional characteristic curve method. For this reason, it's almost never worth using. Many people have learned that lesson and they no longer use this, but unfortunately sometimes lessons learned are forgotten, and we continue to see people in the lithography industry using the characteristic curve method of measuring contrast and getting results that are worth nothing. Anything that causes the development rate to vary with depth into the resist, things like absorption or surface inhibition, will cause an error in the contrast measurements. If you want a good contrast measurement, you have to use a development rate monitor to extract the development rate at a particular point in the resist, not just looking at thickness remaining versus dose. Well, that's lecture 54. Let's look at what we have learned. As always, you should be able to easily and quickly answer these questions. If not, go back and review the material. How is the conventionally measured contrast defined? How is the theoretical contrast defined? Obviously, I wouldn't ask that question if their definitions were not different. When do the conventionally measured and theoretical contrasts give the same results? There's one special case where they do. How is contrast related to the dissolution selectivity parameter N? Well, that ends our discussion about dissolution rate in the photoresist. There's lots more interesting topics, but we only have so much time in this class, so that's all we can cover so far. Next, we'll move on to integrating many of the concepts we've learned so far and think about lithography as a total system. Till then.